I'd like to introduce now Dr. Alexandra Navrotsky, and she is the 2015 MRS Spring Meeting Symposium X speaker. And thank you so much for joining me. Very interested in hearing about your talk. It's titled Energetics at the Nanoscale, Impacts for Geochemistry, the Environment and Materials. So what are some of the key takeaways from your talk?
Very good. Well, the first takeaway, of course, is that although as scientists we've become aware of nanomaterials relatively recently, nanomaterials and nanoparticles are everywhere and have always been everywhere in the environment, in geologic processes, in planetary processes, and they've probably been responsible for much of the catalysis that occurs naturally, perhaps involved even in phenomena such as the origin of life. On the other hand, our knowledge of nanomaterials has expanded tremendously since the late 1990s, perhaps 1997. And for my own research and things I'll be talking about in the talk, I want to stress the energetic, that is the thermodynamic aspects of nanomaterials. We all understand that nanomaterials are much more reactive than bulk materials, partly because they have large surface areas, but more importantly because they often have different structures and really different properties. What we've been less aware of is that much of this reactivity actually has a thermodynamic base. The thermodynamic base occurs because different phases, different crystal structures of a material have different surface energies. And once one is in a regime where the surface energy matters, that is, the surface area is large, one can actually thermodynamically stabilize a different form of a material in a different crystal structure as long as the material does not coarsen. So under constraints, as one often has in nature at low temperature, as one often has in chemical synthesis, as one often has in catalysis, the particle size that forms remains for a long time, but the particles undergo transformations, and those transformations can be thermodynamically driven. So to give several examples, many of the catalysts we use, transition metal oxide catalysts, may actually have a different structure and different reactivity under the conditions at which they operate, simply because they are minimizing their free energy in terms of their surface energies. For example, cobalt oxides used in carbon monoxide, oxidation, and many other reactions. So I'll be talking about those effects ranging then from geologic applications to materials applications.
Fascinating. So if we were talking about some of the next areas of research and some of the issues you face now, can you kind of talk about that?
Yes. Of course, characterization is always an issue, and the ability to do accurate characterization of nanomaterials. Our specialty is thermodynamic measurements by measuring the actual energetics, the actual enthalpies of formation and the actual energetics of absorption of gases and liquids onto nanoparticle surfaces. Perhaps the biggest takeaway there is nanoparticles are in a sense the size of large molecules. They contain hundreds to maybe thousands to maybe tens of thousands of atoms, not millions of atoms. The molecules that are on their surfaces form part of the structure, and perhaps it's important to think of a nanoparticle as a giant molecule, including what is active on its surface, what is absorbed on its surface. So then if one thinks of what nanoparticles will have specific functions, what will operate well, for example, nanomaterials in lithium-ion batteries as an example, one needs to transfer materials through that surface. And one of our major findings, and one of the things we want to explore more, is the energetic competition between water on the nanoparticle surface and the molecules or atoms of interest, the things that are being catalyzed, the lithium ions that are moving in and out. And one of our findings is that a low surface energy generally means a low water adsorption energy, generally means that molecules can move in and out of the nanosurface better, energetically better, kinetically better, and that makes for good activity.
Wow. Dr. Navrotsky, looking forward to your lecture, and thank you so much for being here.